everyone. So for today's sharing session, we'll be discussing about Heaven's Gate in reverse engineering. So yeah, this fancy title actually GPT generated. Okay. So for agenda today, we will be discussing about introduction to Heaven's Gate technique, CTF demo, and Q&A. So what is Heaven's Gate? So Heaven's Gate is a technique that allows the processor to switch from 32-bit mode to 64-bit mode or vice versa. And this technique is more than a decade old, and the last blog I read was from 2009. And yeah, this technique is quite old, but it still occurs for today. If you search for malware sample anywhere, you sometimes you will see some Yara rules detecting Heaven's Gate technique. Yeah, and most of the time, malware developer implement this technique is to make reversal life harder. Like they want us to analyze it, take took more time to analyze it. Yeah, and yeah, this technique could evade detection, and for example, it could bypass traditional sandbox detection of Win32-bit or Win64 API calls. And by evading detection, I mean it's for traditional sandbox. Usually for modern sandbox, obviously it would detect it. It will able to detect this technique. And as I say, the techniques nowadays implemented is just for making reversal life harder instead of the main purpose of evading detection. And how it works, right? So how it works, eventually it will push this 0x33 and then push this code address and then return far return. And this is for this to change the execution processor to 64-bit mode, and for 32-bit mode it puts 23 instead. Yeah, so eventually what this file return does is it will return to this the top of the stack, right? So this next 64 code, and at the same time it will pop this 0x33 into the code segment register. And by placing this value into code segment register, the instruction will be executed in 64-bit mode. And for 32-bit mode, you just need to change the 33 to 23. Yeah. So CTF demo. So we will be solving a crime to get a feedback, and yeah, you can refer to this recording to practice it on your own, because it's quite hard to keep everyone on the same page during live. So this is a crackme and the password is crackmix.1. Okay. So let me put this on. Okay. So I already downloaded the binary zip file. It's here. You can extract it with the crackmix.1 password. And we got this exe file. We'll be using IDEA Pro 32-bit because IDEA freeware doesn't support 32-bit decompiler, but nevertheless it just make our lives easier. You could use Keydraw as well. So give it a while to load. Let me close this. Let me close this. Okay, so this is the So this is the code main function. So you can see this is a prompt, right? So this is probably printf. If you want to verify it, you can click it, and until the end you will see printf. Yeah, so this is printf. We can rename it to printf. And this scanf. So right off the bat we can see that it asks for key, and then we enter it, and then do some operation on it, probably comparing our input with the real input that's supposed to be. And yeah, based on the return value, you can know it's correct or wrong. So that's it. We could try running this binary. Let's say abcdefg hash, and we got it wrong. So now we can try to run it using S32 debugger. We need to debug it, and yeah, just open the binary. All right, so the first breakpoint it was in is actually the system breakpoint. So we could just run it, go to the entry point, and we can run it again, and it's asking for input, so blah, and we got it wrong, just like that. So what we can do is we can search for the wrong string, and this is it. So this is wrong, this is correct. So yeah, you can see this is the printf, this is scanf, and yeah, you can see our input is actually stored at this location, and later on it will call with this function, which means this function is used for comparing our input or checking our input. So what we can do is we go dump it in here, and then we set a hardware access breakpoint. So by setting this breakpoint, right, we could know when our input is being accessed. So we know that at that time our input is being checked. So let me modify it. Okay, so our breakpoint is set. So we could try restart, run input again, a b c d e f g h I, and yeah, so it stopped here. I'm not quite sure why, but this you can obviously see it's not our input, so I will just run it. And yeah, so you can see our input is being reflected on here, which means this function is to check our input. Yeah, it's responsible for our input validation. And yeah, so it's moving some different character of our input into specific register, push it on the stack, and then move more into other register. And then yeah, this for line is eventually doing the heaven's gate technique. And from here you can see this push 33, right, is what is shown in the slide. And this call is actually, when I double click it, right, you can see it's actually calling the next instruction. It's just calling it the next instruction. And after it call it, right, it will add file to the ESP. What this means is by calling a function, we will push the return address, which is this address 7F3, onto the stack. And after that, it moves to this instruction, like it basically add file to it. So you can set a breakpoint here, and yeah, we can restart again, run a b c d e f g h I, run. All right, so we are here. So you can see right now the stack is like this, right? And then when we run it, you can see our return address is being pushed on the stack, which is F8. Okay, F. Oh, I thought it would be F3. It's okay. Oh yeah, sorry. The return address is this line, not this, because if it was this, then it will call again, which is unlimited infinity recursive loop. And yeah, so this is a return address and it's being F5. So you can see from here, if we step into again, it's being F5. So now the latest return address is 7FD, which is here. So what this means is after it's switching the processor architecture to 64-bit, right, it will begin executing the code over here right until this return file. This return file actually just switching it back to 32-bit mode. So you can see the 23 over here. So we could analyze this right on here, but since it was a 64-bit 64-bit architecture convert, we should dump this into a file and then analyze it afterward. So I select the address to dump it over here. It didn't show. Okay, so this is 7FD and this is 7FD. So 7FD to here. Let me double check. Yeah, so this is the shellcode. We save it to file. You can just call it dump.sc. Right, so we got a dump. What we can do now is open our Ghidra. We will Ghidra to do some static analysis on it, and yeah, wait for a while. This is my previous testing. Let me import a new file. So this is it. Right, so it wants us to select a language because it's shellcode. So since this is 64-bit processor executing the code, right, so the code should be 64-bit, and the endianness is little by default. So we could choose this one. Usually the things that matter is size, endianness, and processor. So let's choose this. And it says it's already exists. So can I use it? Maybe this. Okay, dump to. It's okay. So we let Ghidra to analyze it, and Ghidra can't analyze it, so we can press D over here, and it will analyze it, like force decompile or disassembly. And you can see this is much clearer now, but it's still not directly human readable. So this is the compilation, then we choose 1 or 0 based on the correct or false. our goal is to get 1. So we will look at the disassembly view here, and let's see. So first thing, we need to open this, a new file. Let me close this one. This is the live stream. So first is compare. Let me assign the input first. Soft.py. Right, so imagine this is our input. So it's comparing CX to be 0x68. We don't know what is our CX, right? We have to go back to debugger and see. So this 4 is storing our input. This register AL, BL, CL, So you could take a note here. So AL is equal to E, right? E, which is index 4. And let's do the same for other. EL, CL, DL. F is 5, and then this is 0, this is 1. Right? And let's go back. So CL is 0x68. We could do the same, like we could put you could assign, you could create a new variable that set that same as the input. Then we change the byte afterward, which is more easier in my I think, in my opinion. So CL is 0x68. So CL is index 0. So 0x is equal to 0x68. Right? And you can see DL is 33. Right? So DL is 1. So we put 1 here, we change it 33. And next thing is comparing RCX. But it's pop to the RCX. So pop means it take the value from the top of the stack to RCX. And the last push was this push EAX. So we need to take a note first. EAX is equal to what is C, which is input 2, I think, and then BL, EBX, ECS. EBX is D, which is 3, and this is G is 6, I think. Yeah, 6. So let's go back to Ghidra, and we can see it's popped into RCS, and then compare it to 34. So the first push is EAX. I mean, the last push, which is the first value on top of the stack. So this is what the stack looks like for your information. And yeah. So the top of the stack is EX, and it pop its value to RCX. So which means this thing right here is should be equal to 0x34. So after it pop, we can erase it. And next thing is pop into RDX, and then it converts 0x76. So it pop this thing into RDS. So 36. Right, we can erase it. And what's next? Okay, so the next thing is add RS to RBX. So RS is eventually this 2. this is RX, this is RBX. So flag 4 plus flag 5 is equal to 0 SP3. So we have an equation here, but we can't solve it yet because we don't know the potential value of these two. So we move on. And then down here, if minus back, which left only the F4, the flag with index 4, and then it's add together, which means flag plus 4 in fifth character of the flag plus together and minus this 6th character, and then equal to 0x1c. Right, so we have two equations here, and this is a messy mathematics. We could solve it by hand. So this thing, right, is actually equal to minus this. Maybe yeah, like this. And then we can move this thing, right? Let me remove this just for. And we can move this fifth flag 5, right, to here. And then we could simplify it or expand it. This minus is plus, so yeah. And this is eventually S3, and this is eventually and yeah. So we have the value now. We could find the flag for a fifth character. So let's do Python. Put this here. 207 divided by 3, 69. So flag 4 is 69. We now know it. And how about flag 5? Flag 5 is 0xp3 minus 69. 110. So 110, and this is flag 5. And let's comment this out. So let's continue on our Ghidra. And the last thing is just pop this into RDS and then compare with 0. 0 means this is basically a null byte, which oftentimes occurs in C binary. So we do need to carry it. This just indicating this is in the last of the string. Yeah, this is the last byte. So I guess that's it. And then you just compare it and then you jump to the correct, which is the one over here. So we can just print this out. And we get this Heaven's GSI, but this flag actually 6 length of 6, so we could just like this, and yeah, we got the key, which is Heaven. So let's try it. Maybe I open a new. Yeah, is it correct? So that's it for the demo. Now let's move back to the slide. For the slide, it's actually nothing much else. Q&A, you skip here, and this is the reference if you need it. So if you have any other question, you can contact me with Twitter. This is my Twitter handle. So that's all for today. Thank you. See you in the next session. Bye.